Good afternoon, everyone. Welcome to today's colloquium, and happy Halloween. I'm happy to say the colloquium is a sugar-free activity, so you won't gain a pound by being here. First thing, we have Grace Seja, who's the AIAA chair here at APL. I think I said that. Vice chair, sorry. And she'll say a few words about the AIAA. Go ahead.
The special trick that they tell the insiders is you can say AIAA, and then everyone will know what you're saying. It's easier than AA, because there's too many. So hi, everyone. Like Dan said, my name's Grace. I'm the vice chair of the Mid-Atlantic section for the American Institute of Aeronautics and Astronautics. That is a section. There, you could find a map online, but it includes this region. Their sections are broken up geographically. APL falls into the Mid-Atlantic section. A lot of the Mid-Atlantic section works here at APL. So that is, we just wanted to highlight that and the idea of professional societies being kind of your avenue to the technical kind of field expertise where you get that technical information for various fields. AIAA is specific to the aerospace field. There are others as well, and the lab is very supportive of involvement in such things. If you are an APLer, they will pay for professional membership in one such organization per year. So just a brief plug for that, and we wanted to open this up today. We've brought Dr. Gruntman in to speak as a distinguished lecturer and kind of give this as an example of some of the benefits of being involved in a professional society. You have access to these technical experts, and we're really looking forward to Dr. Gruntman's talk today. And so thank you all for being here in person and online.
Okay, thank you, Grace. Now, getting to our speaker, we're very honored to have Mike Gruntman. He's a professor and chair of astronautics at the University of Southern California, which is my alma mater. Go Trojans. His life journey took him from being a child growing up in Teortam, which is also known as Baikonur, missile and space launch base during the late 1950s and the early 1960s. He became an accomplished space scientist and engineer and joined USC in 1990, founding a major educational program in space engineering. Today, it's a nationally recognized and unique astronautical engineering department at USC, with more than 2,000 students who've taken his courses in space systems and rocket science. Dr. Gruntman is actively involved in R&D programs in space science and space technology, having served as a co-investigator on several NASA missions. He's also the recipient of 3 NASA Group Achievement Awards. He's authored and co-authored 300 scholarly publications, including 4 books. His book, Blazing the Trail, The Early History of Spacecraft and Rocketry, won the International Academy of Astronautics Luigi Napolitano Book Award. Dr. Gruntman is an AIAA Associate Fellow and member academician of the International Academy of Astronautics. Let's welcome Mike to the lab.
Thank you, Dan. Thank you, Dan, for your kind introduction. The only small correction, I'm not chair anymore. I was the founding chair of the new space department, but I fortunately got out from this never again experience. So this is a small clarification. Okay, today the talk is about the beginning of the missile defense in the Soviet Union and more globally also, and about the beginning of the air defense that preceded missile defense. So I will start talking a little bit about air defense development in the Soviet Union, and then we will move towards the missile defense and the first intercept of the long-range ballistic missile that took place in 1961. It's a very poorly known event. So I will be concentrating mostly on strategic, non-theater, non-tactical air defense. And this talk is based on the book published by AIAA, which is shown on the right. And I have a number of flyers just right there sitting on this piano. And also there was a short version, only 8 pages in Proceedings of IEEE on this subject. A few copies are also there, as well as my business card, if anybody needs to reach me. So on March 4, 1961, the Soviet Union intercepted non-nuclear warhead of IRBM, Intermediate Range Ballistic Missile. This event was among the most important Soviet achievements in the early age of missiles and space, on par with the launch of the first satellite, of the launch of first man into space, and the first ICBM. At the same time, this event relied on electronics, on radar, and communications and digital computers. These are the areas that historically never looked in the West as something being advanced in the Soviet Union. So this event paved way for emergence of the political, industrial, military, very strong complex in the Soviet Union. And at the same time, this event remains very poorly known, although it plays a very important role in the Cold War. Abundant literature exists on ballistic missiles and space. Now, as I said, very little is known about missile defense activities in the Soviet Union, and at the same time, today, proliferation of ballistic missiles and all state and non-state actors that are using them bring missile defense into focus. This subject remains, missile defense in general, highly politicized, in spite of having consequential importance for the modern world. Arms control community basically argues that ballistic missile threat does not have a technical solution. Missile defense advocates push for achieving or finding such technical solutions to ballistic missiles. Also, missile defense is a very complex technical area, and that requires decades of development, and the capabilities cannot be reconstituted within a couple of years. So it requires long-term planning and work. Also, missile defense provides a very important options for policymakers, and Israel's experience during the last 15 years clearly demonstrates that. So it's, again, very, very important. And hopefully, the fantasy of the end of history is now going away with the recent developments in Europe and the continental war raging there. So this historical background is very important to understanding what's happening today. So the Soviet missile defense was a very important factor in the Cold War. Actually, Soviet expenditures on strategic air and missile defense were between 50 and 100% of the expenditures on the offensive Soviet weapons. So it's a huge part of the Soviet defense establishment. And this first intercept led to the deployment of operational missile defense systems in the Soviet Union, protecting the capital, Moscow, A-35, A-35M, and A-135, which is being deployed today. It also gave rise to a number of associated fields and areas, like monitoring orbiting space objects, space situational awareness in the US terminology, ballistic missile early warning, and anti-satellite weapons and space weapons. All the blue arrows indicate systems that were operationally deployed, not only R&D, but operationally deployed. Also, the Soviet missile defense effort played a major role for the development of the technologies and policies in the United States during the Cold War. And this event in 1961 remains practically unknown. This is a very busy chart. I just mentioned a few words, say a few words about that, and we will touch on this timeline a little bit later. These are the years. The Soviet Union developments are on the upper part, in the United States on the lower part of this chart. So we will concentrate on this top left corner highlighted with the starting of the development of the first guided missile anti-aircraft system, SA-1, the predecessor of SA-2, SA-4, SA-20 today. And then going to the development of System A that demonstrated the first intercept of an IRBM. And then the developments of operational systems in the Soviet Union followed. About the United States, I only mentioned here that in those early years, there was development of air defense systems, then a missile defense started that culminated in the Nike Zeus and Safeguard program that was operationally deployed only for 5 months. This is also an opportunity for a hat tip to APL. In the late 1950s, 1960s, the Talos system was proposed as a land-based missile defense system in the United States. As we would say today, Talos ashore. And it never happened. And then there was obviously work, it's Delta 180 and other related programs in the 1980s, MSX, and other stuff, as you know much better than I do. So APL played a major important role in this field. So now getting to our historical story. The World War II ended. The Soviet Union, after tremendous devastation, pours huge resources to develop ballistic missiles, guided missiles, electronics, computers. This was also the time when the Cold War could have turned hot. There was a major flashpoints in Europe, in Asia, war in Korea, takeover of China by communists, bloody suppression of the rebellions in Eastern Europe. So it was a really dangerous time, with the culminating with the erection of Berlin Wall in 1961. In 1947, Soviet dictator Joseph Stalin ordered creation of a special design bureau, SB-1, for a specific purpose, to develop an anti-ship missile Cometa or Comet. This missile will become known as SA-1 or Canal in the NATO terminology, and it was launched from the airplane and could sink ships from the distance of 60 miles. So he created a special organization to develop that, and the director was, and a few names that I will mention, they're important for the story that I'm telling you about. So the director was Kuksenko, and he had a second in command, young Sergo Beria, the son of the feared head of the Soviet secret police, Lavrentiy Beria. So this is how the career of the young Soviet princeling was built up. And so they were in charge, and by 1953, this was a very successful development, and by 1953, the system had been deployed operationally. And it stayed for 20 or 30 years in operation. But by that time, in 1953, this special design bureau was already engaged in something else, much more important. In 1950, Stalin ordered this SB-1 to develop an impenetrable air defense system of the Soviet capital to protect it against a raid of 1,000 strategic bombers coming from all directions. Now, this design bureau was reorganized into KB1, Design Bureau 1, and Kuksenko and Beria were heads of this development. Now, they brought a deputy developer under the name Alexander Rasplotin, shown here on the left, and this became a huge national effort, development of this system. Now, in addition, the government ordered 30 top scientists from all over the country transferred to this KB1 to help the effort. Among them was an individual named Grigory Kisunko, a rising star in science, young rising star in science. He was a specialist in microwave guides. Again, this is late 1940s. These two people would become the most powerful, the most influential in this extremely powerful KB-1, Design Bureau 1. And Kislyanko would lead missile defense effort until 1970s in the Soviet Union, and Rasputin would concentrate on development of air defense systems. So the concept of interception of an aircraft in late 40s, 1950s relied on the use of two narrow pencil beam radars, one guiding and tracking the target, and the second guiding and tracking the interceptor missile. It was based on the German work on the World War II. To build using this principle, the system against 1,000 bombers would have required 1,000 such pairs of radars. This was impractical. So here, emergence of digital computing offered new possibilities. Again, remember, this is the late 1940s. Rasputin devised a new track while scan radar. So this radar used two fan beams, one by 60 degrees, one scanning in the azimuth direction, and the other scanning in the elevation direction, mechanically scaling. And when they saw the target or the interceptor, they put these coordinates into the digital memory. So the radar consisted of this huge mechanical contraption, 30 feet in diameter, rotating 50 RPM, so basically 1 revolution per second. So these are huge contraptions are doing there. And the CIA named this radar Yo-Yo in all the classified documents that you could find now. So this was and this radar could simultaneously track 20 targets and 20 interceptor missiles. So Stalin died in 1953. Kuksenko, it's a totalitarian country. So Kuksenko demoted. Sergo Beria arrested and banished these leaders of this project. His father, Lavrentiy Beria, is actually executed in the internal Kremlin power struggle, where finally Khrushchev emerged as the leader of the country. The system also renamed into S-25, and this will become known as SA-1 Guild. Again, this is the beginning of all these SA anti-aircraft systems that the Soviet Union has been producing for all these years. Now, the system was, S-25 was huge, and it consisted of 56 air defense sites surrounding Moscow in two circles. The inner circle, 60 miles in diameter, and the outer circle, 110 miles in diameter. Each site housed one air defense regiment, one track while scan radar, B-200, and 60 interceptor missiles. Interceptor missiles were single-stage liquid propellant. So there was this radar that was scanning the defended sector and the field for deployment of these 60 interceptor missiles. The system became operational in 1955. 1 year later, it failed to detect and intercept the only overflight of Moscow by a U-2 reconnaissance plane. This is a photograph of one of the sites from this U-2 plane. So whenever you see this herringbone structure of the roads for the launch field of interceptor missiles, this is SA-1. This is SA-1. And the system stayed operational with the modernizations until the mid-1980s. So Alexander Rasputin and his successors built on the development of SA-1 and developed a series of Soviet strategic air defense systems, SA-2, SA-3, SA-5, which is S-75, S-125, S-200, S-300, 400, S-500. SA-2, actually S-75, brought down the Gary Powers over Moscow in the U-2 reconnaissance plane in 1960. So this was two-stage interceptor. Now SA-2 is shown here. Now, air defense systems were a major tool for the Soviet Union and today for Russia in the geopolitical struggle and competition. And S-300 mentioned here just was in the news for the last several years. It was Iran was trying to buy it. It is in use in Ukraine non-stop, as we know, during the last 8 months. And S-400 was in the news. It was deployed in Syria by the Russian expeditionary forces. And Turkey bought it, creating major issues with F-35 and procurement and all that. So now let us switch gears towards missile defense. Germany, during World War II, developed an A4 or V2 ballistic missile. This is the first modern ballistic missile. It was a technological marvel. 6,000 of these missiles were built and 3,000 were operationally deployed against Allied targets. The moment the missile was deployed, a few visionary scientists and engineers began to think what to do about this, how to protect against the missiles. But nothing could be done. Radar could already see the incoming missiles, but technology to stop them did not exist. So in the United States, there was early studies led by Edward Teller in 1945. Then for the United States Air Forces, Theodore von Karman led a major study. Also, missile defense was mentioned in the United States Army Stilwell, so-called Stilwell report under General Joe Vinegar Stilwell. In the Soviet Union at the same time, there was also a couple individuals who began to explore these possibilities. So there is a smart people in all countries. So when we today look at the world, never dismiss capabilities of North Korea, Iran, and other countries. There are smart folks in many places. Nothing happened for several years. Just the paper studies, feasibility studies. And then in 1953, the situation changed dramatically. So Stalin died in March of 1953. 6 months later, the chief of general staff of the Soviet Army, Marshal Sokolovsky, wrote a letter to the Communist Party urging the development of defenses against ballistic missiles. 6 other war fame marshals, highly influential of the Soviet armed forces, co-signed this letter. So defense establishment tried to respond to that. There was a major meeting with all the luminaries in the defense science field. And the leading Soviet scientists were very dismissive and disparaging about these proposals of the marshals. Say Rasputin, who leads the Soviet air defense program, says it's a nonsense, stupid fantasy. And another luminary, Alexander Mintz, would call it as a stupidity. However, at this meeting, Kisillenko, whom we mentioned, came well prepared with the practical plan, saying that in order to achieve that, you need to have this and that technical characteristics, and this is what needs to be done, how to advance technology. And this has started the ball rolling. Now think about this. This is early 1950s. Very few people thought that missile defense was possible. The Soviet Union was still developing a guided missile against aircraft. Its deployment was 2 years in the future. Now, the warhead effective radar cross-section was 100 times smaller than the radar cross-section of an airplane. And it flew 10 times faster than an airplane. That means a radar had to detect it not 100 to 200 miles away as with the aircraft, but thousands of miles away. So it's a tremendous challenge, and this challenge very often was described as hitting a bullet with bullet, and because there was a very short time for interception, a lot of things must be automated, so the computers must be used. Again, it's 1950s. Transistor was only invented a few years ago. In exceptionally powerful in the Soviet defense establishment design world, Design Bureau 1, there were only 2 individuals who could have practically lead such an effort, Raspletin and Kisillenko. Raspletin got skeptical, and he concentrated on very successfully, he and his successors concentrated on development of air defense systems, SA-2, SA-3, and so on and so forth. Kisillenko, boiling with energy, jumped on this new opportunity. Now, it is important to say that a lot of initial skeptics, like the same Raspletin or this Alexander Mintz, rushed into the new field because the flood of government money was unbelievable that went into this field. So everybody was opportunistic, and they were playing a major role in various aspects of missile defense later. So feasibility studies started first, and then in 1956, the Soviet government authorized Kisillenko to build a defense system for Moscow, missile defense system. And this system became known as the System A, as a test system first, and then to deploy it around Moscow. The experimental System A of Kisillenko consisted of a long-range search radar that detects missile coming from far away, and then it hands over tracking of this missile to the precise tracking radars known as RTNs. And these precise tracking radars were measuring only the distance to the missile, not the angular position. So 3 such radars, shown by yellow, measuring 3 distances, give you 3 equations, and you can determine x, y, and z of the target. The method became known as the method of 3 distances. So Kisillenko wanted to use the existing infrastructure to place these precise tracking radars, RTNs, at the outer ring of air defense system SA-1. And this determined the distance between these 3 radars. And another thing that Kisillenko had to do, he had to build a huge new test range to test such a system. And again, this is 1950s. The system relies heavily on the computers that are, I cannot say non-existent, but their capabilities are very, very small, very weak. So the Soviet Union is a huge country, and the number of test sites were in the Kazakhstan in the center. It's much easier to, when I talk to students, to mention Kazakhstan, because at least in order to explain where, you say, well, this is where Borat comes from, and those who saw the movie say, yeah. So in addition to the existing test sites in Kazakhstan, Soviet government decided to build a new test site known as Saryshagan, and close to the lake Balkhash in the center of Kazakhstan. So the decision to activate it was made in 1956. 100,000 troops of the engineering corps was rushed in this desolate desert, Bedpak Dala desert, to build it. And the conditions were horrible. There was practically no population because of the horrible climate. And the temperatures ranged from -50 Fahrenheit to 120 Fahrenheit in the summer. So it was really very, very harsh conditions. And the system was built in 20 years. This was a major test site with everything that you would expect from a remote military installation, with the thousands of miles of roads, hundreds of houses, thousands and thousands of apartments, and schools, movie theaters, swimming pools, stadiums, hospitals, you name it. So on the Lake Balkhash in the center of Kazakhstan, there was a range head town, Priozersk. And next to that was built this orange rectangle, this long-range radar. 3 yellow squares, 3 precise tracking radars were built there, and they were connected by these pink or magenta crosses, which are microwave communication lines, because there was no time to lay down cables for communication between these sites in the desert. So the communication towers were built, and the interceptor was located somewhere here in the center. The long-range radar, DUNAI-2, was a continuous wave radar with transmitting and receiving antennas separated roughly by 1 kilometer. And what is shown here is a receiving antenna of this radar, and the CIA in the reconnaissance photographs named it hen roost. So this is U2 photograph, and this is from the ground. So it had a beam 0.6 degrees by 16, scanning in the azimuthal direction, and having 2 receiving structures was possible to get the elevation angle. Now, the precise tracking radars were regular dishes, 15 meters in diameter, and each such dish weighed almost 100 metric tons. It was a highly agile system, moving or slewing across the sky 13 degrees per second. That means 15 degrees from one horizon to another, 100 metric tons. Now its radome is shown just right here, and the small radome was for a small radar with only 15-foot diameter antenna for tracking a missile, interceptor missile, and interceptor missile had a transponder, so you don't need a very large radar, a very large antenna. When this precise tracking radar operated, it consumed 650 kilowatts of power, and the entire system achieved relative accuracy of the relative position between a target and the interceptor, 10 meters or 30 feet. So this was the characteristics that were achieved. Now the interceptor missile was a 2-stage interceptor with the first solid stage and then the second liquid stage, and V-1000. And when this missile was launched from a launch pad, there was another additional radar that picked it up from the launch side and followed it for some time and then handed over to 3 precise tracking radars for the final intercept. Now the computer needs to be built. Again, this is the early age. It's only vacuum tube technology. Transistors are still not that really existent. So the computer that was built was, all this program led to a lot of development in the Soviet defense establishment and science and engineering. New institutions, new factories were developed, scientists were educated. So the computer had only 40,000 fixed point operations per second. RAM is 4 kilowords, and external memory 150 kilowords. Your cell phone is, 1,000 times more powerful than that. Communication lines stretched 800 miles across the desert in these microwave towers. They provided 10 to the 5 bits per second, 10 kilobit per second transmission rate with a 10 to the minus 7 bit error rate, which is not bad, actually. The control center controlled the entire intercept. Now, to reconstruct what happened is not that easy because the Soviet government in the 1960s destroyed for secrecy purposes a lot of records of the first tests, but again, still it's possible to reconstruct it. A typical intercept lasted 30-35 minutes to prepare the system for operation. Then the ballistic missile was launched. About 7 minutes were for the detection by the long-range radar and then intercept. The last 14 seconds, the intercept was conducted 100% automatically without a possibility of interference by a human operator. So the intermediate range ballistic missiles, SS-3 and SS-4, were used to test the system. So the late 1960s, the tests began. The first 13 attempts failed. Now, this was a time of the tremendous political and power struggle in the Soviet defense establishment. There was many people who were rivals to Kissinger and wanted to take his program over, and the way to do it, to put down his achievements, 13 failures in advance. It was a very strong argument to argue to Politburo to stop it. And so when you hear about inter-service rivalry, including in the missile defense in the United States, this is not something unique. I gave once time a talk in Israel about this program. Several people who fought for the missile defense system there against the Air Force that was flat against it, telling me, wow, this is just very similar to what we had to go through in the struggles there. So it's again, in addition to bright scientists and engineers, you need to have a very strong and powerful managers. All the stars needs to be aligned to your program, including people with the stars on their shoulder boards. Then only you can get successful in this competitive environment. So 13th test failed. Then on March 2nd, 1961, instead of using SS-3, the bigger SS-4 ballistic missile rocket was used, and it also failed. And finally, the second launch of SS-4 on March 4, 1961, succeeded. So the Strategic Rocket Forces fired this IRBM, and 6 minutes before the intercept, Dunai-2 detected the missile about 600 miles away and 300 miles in altitude. So after then, 3 precise tracking radars, RTN, took over the tracking. Now, the computers are based on vacuum tube technology. So since not everybody in this audience goes to the museums and sees how these vacuum tubes work, so those who had some experience with that will tell you you cannot turn them on instantaneously. It takes 10, 15, 30 seconds for them to heat up to the tungsten wire, would start to emit electrons in there, and then will start operational. So the Soviet engineers knew that they are not very reliable, so they had an additional. So what happened that during this intercept already is going on, and the computer is preparing to calculate, to compute the intercept or fire solution, one of these vacuum tubes blew up. So engineers had a special rack when they had a number of these vacuum tubes in a warm condition. So an engineer runs there, grabs one of them, I don't know whether they use gloves or by bare hand, and just runs and just replaces it in the right place. And they succeeded in time to reboot the entire system for the intercept, so things work. And 44 seconds before the interceptor missile, V-1000, is launched, I'm sorry. And then the final 14 seconds, automatically the intercept occurs. The miss distance that was achieved was only 30 meters or 100 feet. And the intercept took place 37 miles from the interceptor launch site and at 15 miles altitude. Now, this is a non-nuclear intercept. Guidance is not there to hit precisely the warhead. So approaching the incoming warhead, the interceptor deployed 16,000 one-inch spheres. And they formed a disk, and a few of them hit the incoming warhead. Each sphere consisted of a stainless steel envelope within the explosives. And then there was a core about, so it's a 1-inch diameter, and the core about 9 or 10 millimeters was made out of very hard material, carbide, tungsten, and something else. So a few of them hit this warhead and took it down. So it's a successful intercept. The photographs are shown on the right. They were recovered. The mock-up of the warhead was recovered after the successful intercept. For the next 2 or 3 years, the intercept test continued. The total was 11 more were conducted, and 1/2 of them were successfully intercepted. It is important to say that during the very first intercepts, already the Soviets began to test the penetration aid technology. So the struggle between the penetration aid and missile defense started almost on the day one on missile defense. So the struggle between the sword and shield, again, from the day one, whatever is being invented, at the same time the countermeasures are coming. So it's always important to keep in mind. So this has happened in the missile defense. So now getting again to this timeline. So let us recap what happened. In 1960, 1 year before this intercept that we talked about, the United States Army intercepted 4 tactical missiles at White Sands. Honest John, 2 Corporals, and one Nike Hercules. So after that, in 1961, the Soviet Union, in non-nuclear way, intercepts IRBM. By that time, both the Soviet Union and the United States already came to the conclusion that non-nuclear intercept is not practical. You need to have guidance is not there yet. You have to have a nuclear intercept. So in 1962, the United States demonstrates a simulated nuclear intercept. Basically, the interceptor should fly within 200 meters of the incoming target and to send a command to detonate a nuclear charge at the right time. So it was demonstrated for ICBM now by the United States. So after that, the Soviets deploy their nuclear armed system, A-35, A-35M. The United States deployed Safeguard for 5 months in 1975-76. Research and then the United States terminated operationally deployed system. Soviet Union continued until today to have the operationally deployed system. So the technology development continued, and the guidance has been improving every day since those early days. And in 1984, there was a homing overlay experiment. The United States basically increased the area of the interceptor from a small warheads to 13 feet or 4 meters in diameter and intercepted coming ballistic missile. If you go to the Woodward-Hazy National Air and Space Museum, next to the Dallas airport, at the ceiling, you will see this HOE contraption. After that, US continues to develop its technology. Nuclear missile defense system basically got into place in 1990s, and development continued. So we reached the point where the intercept, hit to kill intercept is possible. So this is from one of the tests in 2007. Today we have operationally deployed interceptors, hit to kill, kinetic kill interceptors deployed in Alaska and the state of California. What happened in the Soviet Union after all these heroic days? The Soviet Union disintegrated in the early 1990s. The Sarishagan test site turned out to be in an independent state of Kazakhstan. So the government consolidated air defense and the missile defense industry into the huge conglomerate, Antey, and now Almaz, and now Almaz Antey. In the Sarishagan, the number of personnel shrank from 15,000 to 1,500 or something like that. A few sites or components of this test site is being leased by the Russian Federation for tests of A-35 and its modifications, and other parts deteriorated, as you could see here. Now, Kisunko, the person behind the first intercept, System A, the person behind A-35, the first missile defense system, and the first phase of the development of its modification, A-35M, got out of favor and was fired in 1975 in the vicious power struggle inside. After that, he wasn't allowed to be anywhere close to the missile defense effort in the Soviet Union. So it's again a very vicious story. And the relations remained so bitter that when he passed away in 1998, government even didn't pitch a little bit money to put a tombstone on his grave. So it's the veterans had to collect money. So finally, on the concluding remarks, not much changed in the conceptually about missile defense. As Chief of Naval Operations Admiral James Watkins in 1983 described it, wouldn't it be better to protect the American people than to avenge them? So this question remains important today. The first American and Soviet intercepts of 1950s, 60s, and beyond demonstrated that technological challenge can be met. A bullet can be hit by a bullet, so it's done with an increasing accuracy today. We have a direct-to-kill kinetic intercepts. Now, again, it is important that missile defense offers tremendous policy options to the government leaders, to national leaders, and Israel again demonstrated this dimension of missile defense dramatically during the last 2 decades with very successful intercepts on the tactical level. And many countries today realize that and rushed into the development of some way informed missile defense capabilities. The People's Republic of China, India, South Korea, Saudi Arabia, Gulf states, Turkey, and even our enlightened friends in Europe got warmer to the idea of missile defense rather than protesting deployment of missile defense. So more than 50 years ago, the pioneers blazed the trail in search of technical means for defense against deadly ballistic missiles. As life goes on and new threats emerge, the eternal competition between the sword and the shield continues. Thank you for your attention. I'm right on time, right?
Yes, you are. Questions for Mike from the audience here? We have a few from the online audience, so why don't I go to them, what these folks think. Oh, there is one. Okay, go.
Quick question. I can't remember, a couple slides prior you talked about, even from the get-go, that they started testing against countermeasures like decoys and jammers. How much of that was essentially them testing their own penetration aids versus essentially being able to ascertain what the U.S. was doing and trying to figure out whether their interceptors would be able to go after our ballistic missiles?
So the question is about when the penetration aids were introduced during the early testing, whether they were parts of the developing of penetration aids or understand what the United States could do. It's very hard to tell. I think it's always a combination because, again, the logical people and smart people are everywhere, and the Soviet organizations that were developing intercontinental ballistic missiles were also brought into this picture. I have to mention that administratively in the Soviet Union, ballistic missiles and space and missile defense were in different stovepipes. Organizationally, administratively, reporting to the different ministers, but still there was some crosstalk there. And a leading Soviet developer of ICBMs, for example, in the Ukraine, that's today, again, in the news occasionally being bombarded as a huge march, was tasked in 1963 already in the official requirements for the next ICBM that they were developing to include US missile defense penetration measures. But as always, it is a combination of different pressures. In Soviet case, it was also an attempt by a rival faction to discredit Kissinger and take over funding and everything else to show that what he does is not good enough. So it was various things, but in general, again, as the scientists and engineers who are honestly involved in the program, not on the political side, they all understand that there could be measures and you have to push this technology.
Okay, question from the Zoom audience from David. Why were the precise tracking errors range only? Was it because even small angle errors would result in large position errors at the extremely long tracking range?
This is exactly correct. The technology at that time in angular determination of the position of a target was not good enough. And to overcome that, the idea was to introduce this 3 distances method. And when it was realized that it's still not good enough, then all operational systems went back to their regular radars that are detecting not only the distance, range, but also angular positions.
Okay, thank you. More questions from the audience here? No? Question from Tracy. Can you say a bit more about Russia's export of its SA-300, 400, 500 systems to other countries? Which countries have which systems now?
I never specifically looked into that, but a lot of countries. Now about S-300, there is something very interesting. There was another country. Turkey was not the first controversial country in the NASA world, in the NATO world, sorry. In the NATO world that acquired the recent system. If I'm not mistaken, in the early 1990s, Greece purchased S-300 with a tremendous uproar, with all these, obviously, people in the defense establishment on the NATO side. So it's even among the European allies, United States, there was this technology. And by the way, this purchase by Greece tremendously helped financially to preserve in the crumbling Soviet Union of this air defense industry. They needed money desperately in those days, so the prices were also low. Now, as we know from the news, for example, I think Slovakia and Slovenia transferred to Ukraine S-300, so it's a lot of countries in the Soviet space in the past during the Cold War had 300s. Which countries else, I simply do not know. It's not my specialty, but in general, air defense export was a major tool in the geopolitical, diplomatic struggle between the 2 blocks. Providing them to the friendly regimes was always very important.
And were the 400 and 500 systems exported?
For 400, we know Turkey. Turkey bought it. 500, it's the latest. It has never been exported. It's only, I'm not sure how much operationally when it is in the Soviet Union, in the Russian Federation, but it was in the tests for the last, 5-6 years already.
Okay. Let's see, there's a question here from David. Can you provide your charts to APL employees? Would that be all right?
Yes.
Okay, very good. I
will email you the PDF.
I can distribute them as you like. And a question from Samuel. How vulnerable were or are these systems to jamming?
So this was exactly the first penetration aids tests, and there was 3 types of tests. One was using special coverage of the warhead, which absorbs radar signals. And again, this is 1961, so it's again, people were thinking almost the same, that not to be arrogant, just should look what people did in the past. A lot of stuff was done in the past. Deployment of the decoys, and the third, deployment of the active radio transmitters on the decoys, especially to jam radars. So it was from the very beginning, and there was a lot of work went into collecting statistical data to be able to distinguish the warhead from these accompanying decoys or jammers. One of the key technologies that was pushed by Kissinger in modernization of operationally deployed A-35 to A-35M was to look at the polarization of the radar signals when they are being reflected. So he hoped that it will be a major breakthrough against the penetration rate technologies that which was developed significantly in 1960s by the United States, and it actually led in 1968-69 to a period that was known as the crisis in the Soviet missile defense. And again, one of these fallouts was that 7 years later, Kissinger was fired and the new people came to the leading position, and that crisis was caused that now a ballistic missile target, instead of being as in 1960, consisting of two parts, the last stage of the ballistic missile and the separated warhead, now was a sausage, as they were saying, 300 miles long, 30 miles in diameter, filled by thousands of decoys, and dipole decoys, and dozens of light and even heavy weight decoys that are not just dipoles, but resembling a warhead. So this was a major struggle. And again, this is the struggle remains today for missile defense. And the more sophisticated the adversary, the more difficult it is to distinguish between the real warhead that needs to be taken out and decoys. It's in particular when it's a non-nuclear intercept, because one of the ideas behind nuclear intercept is by exploding a very large nuclear charge, you can wipe out the field, remove a lot of decoys, especially light decoys and dipoles, and there's only the real warheads would be remaining to be intercepted.
Okay, one more question from the audience.
Sorry, I had read recently that there's some speculation that in the early days of the American missile defense system, it was treated more as a possible carrot to be traded away during arms control discussions during the Cold War, rather than a serious thing to be developed. Were there that kind of policy discussions that you know of being handled on the ground side?
I'm not familiar with anything specifically.
Mike, can you repeat the question, please?
Oh, sorry. So the question is whether that in the United States, development of missile defense, some think, I disagree with that, but some think was done not for the purposes of missile defense, but using something to be traded during the arms control negotiations, whether something like that was done in the Soviet Union. I'm not familiar with such specific things. I'm sure some people in the defense establishment thought in this way, the same as in the United States. There was honest differences in opinion. Again, as I mentioned in the very beginning, many people in the arms control community believe that there is no technical solutions for ballistic missile threat. Again, I'm saying it's a neutral way and not arguing. And in the missile defense side, people look for such solutions. So I'm not familiar with that specifically. I can easily imagine that there were some people who were thinking in this way, although many things are becoming irreversible. When you establish a very huge, powerful structure, which is dozens of military design bureaus, factories, you cannot close them. So they need to continue to do work. I have spent some time recently in the archives, working on some certain archives that Hoover Institution acquired of some top-level Soviet functionary. And was interesting there, he mentions that for the military-industrial complex, they were required to have like 3% increases every year in their output, whether it's needed or not. And because of the very powerful regional party bosses they could always go to the Kremlin, to the very top, and not based on merit, but based on political non-merit considerations, argue that certain programs should be continued. And this was happening, always was happening. So this was a typical situation. So it's, even if somebody thought that it could be used as a trade, the program, as there was a saying among Soviet functionaries, the train has left the station. There's no way to turn it. So even whether it's needed or not, the money would be coming, PhDs would be defended, new FFRDCs or UARCs would be established.
Okay, thank you, Mike. Let's thank Mike again.
Thank you.